Tonight, Technosignatures, the scientific search for evidence of technology beyond Earth. We'll define what is testable, summarize current limits, compare competing strategies, address false positives, and list the instruments and surveys coming online that could move the field. What counts as a technosignature? Operationally, it is any observable effect more likely produced by technology than by known astrophysical or geophysical processes. Principal categories include narrowband or drifting radio carriers, broadband or pulsed optical near-IR lasers, engineered transits or swarm occultations, artificial illumination on night-side hemispheres, anomalous atmospheric molecules in exoplanet spectra, inconsistent with known geochemistry or biology, high mid-IR waste heat excess from large energy harvesting, non-gravitational accelerations with engineered drive profiles in small bodies or probes. Why radio remains central? Narrowband radio tones at centimeter-to-meter wavelengths are cheap to generate, propagate efficiently through the interstellar medium, and are spectrally distinctive. Nature rarely produces sub-Hertz-wide carriers. Technology does. Modern backends can search billions of channels with Doppler drift correction for relative motion. The method is mature, scalable, and falsifiable. A candidate either repeats from the sky position with the expected drift, or it does not. Current radio constraints. Large single dishes and phased arrays have surveyed hundreds of thousands of nearby sun-like stars and wide swaths of the galactic plane for continuous or drifting carriers above typical effective isotropic radiated power. EIRP, thresholds over 10 chords squared 10 chords 10 chords 10 W at distances of tens to hundreds of light years. No repeating extraterrestrial signal has survived interference vetting and reobservation. This rules out Earth-class, always-on beacons in the nearest neighborhood, but does not constrain narrow, intermittent, low-duty, or highly directional transmitters. Optical and near-IR laser searches. Short pulses at nanosecond to microsecond scales can outshine host stars momentarily. Fast photometers and spectrographs scan for coincident photon bursts across multiple detectors to eliminate cosmic rays. Upper limits now exclude high-repetition, high-energy laser beacons in thousands of systems, but sensitivity to sparse, low-duty pulses remains limited by sky coverage and cadence. Waste heat and mid-IR excess. Any civilization using large fractions of a star's output must dump entropy. That waste heat peaks at mid-IR wavelengths for blackbody temperatures of a few hundred Kelvin. All sky IR surveys have placed population-level limits. Galaxies and stars with extreme mid-IR excess attributable to galaxy-scale energy capture are rare to absent in current catalogs. At the stellar scale, most strong mid-IR excesses are explained by dust, protoplanetary disks, or post-AGB shells. The dialectic here is clear. Thermodynamics demands waste heat. Astrophysics provides many natural IR sources. Disambiguation requires spectral shapes, temporal behavior, and spatial morphology inconsistent with dust. Engineered transits and megastructure claims. Transit light curves with a periodic depths or complex substructure have prompted speculation about swarms or structures. Follow-up typically finds natural explanations: dust clouds, cometary trains, or star spot activity cycles. The lesson is methodological. Impose priors that favor known astrophysics, require achromaticity tests, multi-band coverage, polarization checks, and spectroscopic monitoring before invoking engineering. Artificial illumination hypotheses. The night side of a tidally locked exoplanet could host artificial lighting detectable as a small phase curve anomaly at optical near-IR wavelengths. Present telescopes lack the photometric precision at required contrast for most targets. Next-generation direct imaging missions could set meaningful limits on city-scale luminosities within a few parsecs. Until then, this remains a calculated possibility, not a constraint. Atmospheric technosignatures versus biosignatures. Industrial molecules like chlorofluorocarbons, CFCs, have spectral lines in mid-IR windows and no known abiotic sources at high abundance. Detecting them requires high signal-to-noise, high-resolution spectroscopy, and favorable targets. Dialectic. Even if detected, contamination from instrumental systematics, stellar variability, or overlapping natural lines must be excluded. Conversely, purely biological gases, e.g., oxygen plus methane disequilibrium, can flag life, but not technology. Combined gas suites, temporal variability, and surface reflectance features improve attribution. Non-gravitational accelerations and probes. Objects with sustained accelerations not explained by outgassing, radiation pressure, or tides invite scrutiny. To date, each high-profile case has yielded natural explanations within uncertainties or remained ambiguous. Standards are straightforward. Demand in situ, tracking precision, outgassing constraints, and laboratory benchmark material models before implying control systems. False positives and interference controls. Most detections in radio are terrestrial: satellites, aircraft, microwave ovens, or self-generated intermodulation. Robust protocols require on-off scanning, source field versus reference, multi-beam null tests, polarization checks, and independent facilities. Candidates must reappear at the same sky coordinates across epochs with consistent Doppler drift compatible with celestial dynamics. Data volumes and machine learning. Modern surveys produce petabyte-scale spectrograms. Machine learning classifiers flag anomalies but can also learn the interference environment instead of the sky. Governance is practical. Publish labeled interference sets. Perform blinded injections of synthetic signals. Mandate independent replication on raw voltages, and keep human interpretable features in the loop. Why null results are informative. They constrain luminosity functions, duty cycles, and beaming of hypothetical transmitters. Combine non-detections across bands, map out regions of parameter space where beacons are absent or rare. This converts silence into quantitative priors for future instrument design and time allocation. Competing search strategies, the dialectic. Strategy A, deep, narrow, stare long at nearby, sun-like stars to maximize sensitivity to weak, intermittent signals. Trade sky coverage for repeatability and Doppler coherence. Strategy B, wide, shallow, sweep huge portions of sky quickly to catch rare, bright events. Accept higher false positive rates and lower per target depth. Strategy C, targeted synthetics. Observe transiting planet hosts with measured radii and temperatures. Coordinate radio and optical windows during predicted high-interest phases. The community increasingly blends these, scheduling tiered passes: a wide scout, a targeted confirm, and a deep stare. Current survey landscape: high level. Multi-beam radio backends on large dishes and interferometers, scanning 1 to 12 gigahertz with drift rate correction, spanning spacecraft class to planet class accelerations. Optical, near-IR photonics for nanosecond scale pulse searches at selected bright stars and clusters. All-sky mid-IR reanalyses comparing spectral energy distributions to dust models and flagging outliers for spectroscopy. Coordinated campaigns on known exoplanets during transits and secondary eclipses to probe atmospheric molecules and night-side emission. Decision criteria for claims. A technosignature claim requires: 1. Reproducibility from the same sky position across multiple epochs. 2. Elimination of local interference through spatial filtering, side lobe checks, and independent observatories. 3. A signal model with celestial Doppler behavior. 4. Consistency with energy, engineering, and information constraints. And ideally, 5. Multimodal confirmation in a second band or method. Near-term instruments and what they can decide. Next-gen wideband radio backends. Order of magnitude increases in channel count and drift rate coverage will reduce misdetections of fast accelerating sources. High-throughput optical pulse arrays. Larger apertures plus faster detectors will cut upper limits on pulse beacons by factors of a few across thousands of stars. Mid-IR spectrographs on large telescopes. Higher resolution will separate dust continua from narrow industrial lines, testing the waste heat plus line hypothesis on the best nearby targets. Direct imaging exoplanet missions. Concept stage. Coronagraphs and star shades could reach contrast needed to test night-side illumination and map atmospheric technosignatures at a handful of nearby rocky planets. How this intersects with mainstream astrophysics. Radio surveys map transient interference in pulsars. Optical pulse hunts refine detector timing. Mid-IR outlier searches improve dust models. Exoplanet spectroscopy advances, line lists, and cloud physics. Even in the absence of detection, each effort feeds conventional science. Cost, time, and practicality. Many technosignature searches are piggyback programs on existing facilities using commensal backends and scheduled exoplanet observations. Marginal cost is modest compared to flagship missions. The primary constraint is disciplined data handling and calibration standards. Policy on openness and replication. Release raw and processed data with metadata sufficient for reanalysis. Provide open candidate lists with sky positions and times. Invite independent follow-up before claims. Document pipelines, and apply pre-registered decision thresholds where feasible. What a positive would look like in practice. A narrowband radio tone detected independently by two facilities, repeating from the same right ascension/declination on multiple nights, with a Doppler drift curve matching a planet-like orbit around a nearby star, unrelated to known spacecraft or satellites, and persisting through on-off, multi-beam, and polarization checks. Secondary confirmation could be a coincident optical pulse or a periodic modulation encoding information. Absent multimodal support, the burden of proof is repeatability and exhaustive interference exclusion. Risks of premature claims. Media amplification of single epoch anomalies damages credibility and time allocation. The mitigation is procedural. Strict multi-site confirmation before public announcements, and a culture that values null results and retractions. Parameter space remains large. Weaker transmitters, lower duty cycles, higher frequencies, and engineered signals designed for different discovery priors are all possible. The disciplined approach is incremental. Expand sky coverage, deepen per-target sensitivity, improve interference rejection, and coordinate multi-band campaigns on known planetary systems. Detection would be unambiguous only under stringent confirmation. Non-detection remains informative by shrinking viable scenarios. Technosignature science tests a clear proposition. Technology leaves distinct, detectable footprints. So far, surveys have not found a repeatable extraterrestrial signal. The result is not failure. It is a map of where signals are not. The next instruments will enlarge that map or put a marker where a transmitter, a laser, a waste heat glow, or a chemical line should not be, unless it is. Coverage continues as new data are released, candidates are posted, and independent rechecks report in.